So I am a climatologist, but I did spend, I always say 12 years, yeah, probably was more like 14 or 15 in the energy industry, doing lots of long-term planning, fuels forecasting, right back when we got first wind farms. How do we get this into the market? How can we offer wind at a real price? I was involved in a lot of different projects, but my main raison d'etre there was forecasting wind and water on a range of timescales. And so since then, I got some lovely deep south funding, which I'm very grateful for, and have had 3 lovely years at University of Otago looking at climate change impacts on the energy system. The last few years at Meridian Energy, I was modelling the electricity system out to 2050, and so I took the model with me from Meridian. They kindly gave me a licence to use it, and took that with me, and then got a whole load of wind and water forecasts from NIWA and put the 2 together to see what the impacts were. So that's what I'm going to talk to you about today. So we'll hook into it. No,
Is it
I hook it forward.
Hopefully,
I was just going to hit the down arrow, but it doesn't seem to be able to do the space arrow. Oh yeah, cool, thank you. So so do remember I made this for the energy people at the conference, but hopefully you'll all get something out of it too. So the big problems in the energy are, we know that we're going to double electricity demand in the next 30 years, possibly more, and that we have to build 2 wind or solar farms a year to cater for that, which we are not quite coping with. We've built about 1 a year for the last 20 years, so we've got a lot more to do. We know that intermittency is increasing with all the intermittent renewables, and we need to firm up intermittency, and we need a tool for that, particularly that now that Lake Onslow's gone down the gurgler, and a solution for dry year winters, because our hydro is pretty good at firming up the intermittency at the moment, but in the future there won't be enough of it. And I have no new hydro in my modelling. People just don't have an appetite for flooding big valleys anymore, which is a good thing, but it does leave us with this problem. Distributed energy is becoming massive, and we need to find ways to deal with that. These are the big issues really in the electricity system at the moment. But on the other side, fuels are changing too, and we are not currently incorporating this in energy modelling in New Zealand, and I think we need to. And so this is my stab at showing how we can do that. And I've already been approached by lots of people wanting these data sets so they can put it in their energy modelling. So our fuels are changing. So in the modelling that I do, and that there's about 6 or 7 national electricity models around the country that people are using, and we use, we've got more than 100 years of river flow records in some places now, wind less so, but 50 years of good wind record, and we can synthesize data for longer records. And so that is the information that goes into the electricity system modelling to tell us, A, what we can generate next February, but also how much kit we need to build going out to 2050. But it's changing. So this is Lake Coleridge daily inflows out to 2050, and you can see it's clearly trending upwards, and we need to incorporate that in our modelling. So today I'm just going to talk to you about how wind and water have changed in the last century, what we can expect in the future, so projections of changes to river flows and wind from NIWA, and then put that information through an electricity system model and look at the implications of that. This is a really good place to just give some acknowledgements. So thank you very much to the Deep South Science Challenge for the funding. It's been fantastic. Thank you, Meridian Energy, for the electricity system model and the background data from that, and particularly Grant Telfer, who's the model developer, who's been invaluable. River flow projections come from Christian Zammit at NIWA, and wind speed projections from Richard Turner at NIWA. So let's hook into how wind and water has changed in the last century. Start with a big umbrella view. This is total annual wind energy at 20 existing or proposed wind farms. Most of these wind farms have been built by now. A lot of this data is synthesized. We don't have really good long-term wind records, but it's synthesized with a great deal of thought, so that's reasonably accurate. And if you bung a linear trend through this, you would say that we've had a 2% decrease in wind speed over that time as a long-term linear trend. There's a high amount of variability, as you can see. This is just annual wind. There's a lot of variability, and that's not a statistically significant trend. However, it does fit in with the great global stilling, which I'm not sure if you know about that, but wind speeds globally have been decreasing at about 2% a decade for the last 50 years. and nobody knows why. So, and it's actually at odds with climate change projections, which are more about more wind, more heat, more energy in the system, and more wind. So it'll be interesting to see how those two dissect, because all the projections are for increasing wind, and yet we're experiencing decreasing wind. And 2% is average. So down the east coast of Australia, it's massive. It's more than that. It's about 5% a decade. So it's quite significant. So watch this space. This is total annual hydro energy at all our existing sites in gigawatt hours from for the last 90 years. Once again, high variability, but if you believe the linear trend, about a 2% increase in water coming in annually. The variability is high. It's not a statistically significant trend, but it also fits in with our general movement towards a bit more water. Warmer air holds more moisture. We're going to get more rain, and it does rain. So that's just a big umbrella view. Let's drill down into that a little bit. What about seasonal cycles? No, sorry, not seasonal cycles, shorter cycles than the long-term trend. So this is the exactly the same picture as before, the wind energy with the interdecadal Pacific Oscillation mapped over the top of it. I'm sure everyone in this room knows what the IPO is, but it's a 20 to 25 year cycle in our weather where we get 20 years of lots of El Niños and then 20 years of lots of La Niñas, roughly. And so in the El Niño phase, we get lots of southwesterlies, which is more water into the hydro lakes. And in the La Niña phase, we get less water into the hydro lakes, and there's about a 5% shift in mean flows between the two. And that's in wind. And if we look at it in the water side, it's about a 7% shift in mean flows between the two. One of the reasons this is really important, and I'm not really talking about climate cycles here, I'm talking about climate change, but the reason I bring this up, particularly for the energy sector, is that the whole New Zealand electricity market has been predicated on a dry, less windy phase of the IPO. And so if there's about 4 or 5 cycles of the IPO in the observed record, but there is evidence of the IPO going further back in paleo records. And so if we believe that we are just about to head into a wet and windy 20 years, that will have significant ramifications for the electricity market, which has totally existed on this drier, less windy phase. So we may see depressed prices. That might be one implication, and that will impact the return on investment of all this kit that's being built recently. So it's just something that we should think about. I've actually got a funding bid in at the moment to look at climate cycles and the energy industry, but it's very hard to get funding in New Zealand, so we'll see. So let's go drill down even further at seasonal cycles. So this is a very pretty picture, but there's a lot going on. It's 100 years on the bottom, on the x-axis, and weeks of the year up the right-hand side, from September at the top to May at the bottom. I've chopped off the winters because I'm more interested in the summers here. And so what you can get from this graph, so if every little square is a week of inflows into Lake Pukaki, if the colour of the square is sort of reddy purple, then it's something like 400 cumecs average flow for the whole week, which is quite a big flow. And if it's a dark green square, then it's less than 20 cumecs average flow for that week. So you can see that the big inflows come in the summer. We know that, about half of that is snowmelt and half is from just increased rainfall in the summer. And so if you were managing this catchment in the 1920s, you would have expected your big flows to come between sort of January, February, March. And if you're managing them more recently, you might expect your big flows to be around in December, January, February. So there's been a significant shift in the cycle. If we look at that exact same picture, just in a different format, this is July to June along the x-axis, and the dark blue line is the average of the first half of the last 100 years, weekly inflows into Lake Pukaki, and the light blue line is the average of the last 50 years average flow into Lake Pukaki. And you can see that there's been a significant 25% drop in inflows in February. And I first noticed this when I was working in the energy industry a few years ago, and it was my job to set up the contract position for the next year. So I had to use any tools I could. I mean, there's no meteorological forecast for that time period. There's no climatological forecast for a year ahead. So all I could do was look at past history and say, based on past history, we're going to get this much water, therefore we can sell this many contracts of electricity to our customers. And we covered ourselves for the 5th and 95th percentile of past inflows. And outside that, we would have to buy off the spot market, which is massively expensive. And so year after year, we'd get to February and there wouldn't be enough water and we'd have to buy off the spot market to supply our customers. And so I looked into this and we changed our methodology because of this. So if you work in the energy industry and you want to adapt for this, or any other industry actually that uses water, I'm doing some work with some irrigators in Canterbury, so they've got the same problem, then how do you go about it? So this is a
quick question on that one, Jen. How reliable is the data going back?
Oh yeah, no, there's big questions around it. But NIWA's done a huge amount of work on that data set. Yeah. So this is the this data here is the Electricity Authority HND data set, which Roddy Henderson in particular has put a huge amount of work into. But there's some really big, I asked the EA a few years ago to take out 1931, because there's this massive, yes, there, that big flood in 1931, which I looked at a whole lot of proximal catchments and it wasn't there. And I said, I don't think this is real. And you could imagine in 1926 to measure the river flow, they would have ridden out there on a horse, stuck a stick in the river. And if it was raining, they probably didn't go out. So yeah, no, there's if you look at the raw data, which I have, there's big gaps and big flat lines. Roddy's done and his team have done an amazing job. But yeah, there's definitely questions. When I was doing seasonal forecasting, I wanted to use a long record, but I started at 1940 because I just didn't trust the 30s. So yeah, definitely proviso. In all of this, there's provisos around error. Oh, sorry, I forgot to use that. Just yes, no, definitely provisos around error. So I did this a few years ago, and since then we've had a couple of bigger events in February. So yeah, it definitely changes over time, and take it with a grain of salt. A lot of the stuff that I do when I give it to energy modelers, they go, "Oh, that's too big," and I say, "Well, halve it, but keep the relationship between different regions, east and west, north and south. Keep the relationship between different times of the year. But if the numbers are too scary for you, then just bring all the numbers down again a bit. But we need to, there are changes between spatially and through seasonality that we need to start acknowledging. Yeah. So here we've got 90 years, almost 100 years of Februaries. So it's a time series of February data, with each dot being the average flow for that February. And we can see a clear downward trend, and we want to put this, we want to guess how much water we're going to get next February. So there's sort of three ways you can do that. You can take the entire distribution with the mean in the middle and say, well, next February we're going to get something along that range of possibilities. But that's pretty wide, and what I found was that I was getting it wrong year after year, guessing what my February inflows were going to be based on that. The second thing you can do is take the climatological normal, which is the average of the last 30 years, which is used, but was set up by the World Meteorological Organization a few decades ago to acknowledge that the climate's changing. 30 years is deemed long enough to capture some of the big ups and downs, but not so long that we're actually relying on really old data. And the mean of the last 30 years is said to be our best guess of current climate. So you could just use that, but if you do that, you're going to miss out on a whole bunch of big ups and downs that you actually want to acknowledge in the record. And the third thing you can do is called statistical decomposition. So you decompose your data down into a long-term trend, seasonal cycle, and noise. Then you take out the long-term trend and put it back together. And this is detrending. And this is what I did with the energy data that I was using operationally. So what you do is take each of those black dots and bring them down commensurate with those red arrows until the mean of your early data has the same mean as your more recent data. And the result is that it looks like that. So I'll just do that again. That's your original data. And this is the detrended data set. So that's what's going into energy modelling to set up contract position at Purdie Energy. And multiple people have asked me to come and teach them this so that they can put it in. Now, I've talked to ECAN a few weeks ago about this, and their objective is to look at return periods of floods and whether they're changing. And this is not the technique for them, because that's, if you're only interested in floods, then that's grabbing some of those really big floods, questionable, sure, but there's some, through the 50s there's some, and 60s there's some big floods, which you could probably believe, and bringing them down in size. So you don't want to do that. So it depends on the application. Anyway, I think I've done enough on past data. Let's get into some future projections. So how do you make future projections? Probably everyone on this room knows this, but the energy people didn't, so I'll quickly whip through it. Start with a global circulation model, global climate model, and which has about 100K grid. They're coming down all the time in grid size, but about 100K is about right at the moment. 100K grid across the surface and through the atmosphere. And then they project things like sea level pressures and sea surface temperatures and geopotential heights going out into the future. Then NIWA grabs that data. They take the 6 best models. So there's about 30 global models being run around the world. NIWA grabs the best 6, or what they think are the best 6 models, and they dynamically downscale that using a regional climate model to about a 12K grid. They then interpolate it using spline interpolation techniques to a 5K grid, and then that goes into a rainfall runoff model, which has a digital elevation model, land cover, snowpack, and everything. And the wind data is put through a wind flow model, also with that digital elevation model in it. So out of that, we get daily projections from, well, the model is run back to 1970, but I got daily projections from 2006 to 2100 for every catchment down to Strala 2 in New Zealand, and I forget how many wind regions, but quite a lot of wind sites. And then I chose out the ones that were really relevant to where there were wind farms, where there was hydro, and proceeded with that. Now, I haven't put a slide in here about error, but you could give a whole presentation on error in this. Suffice to say, the models are run back in time, but there's a bit of there's an iterative process. Bias correction involves running the model back in time and then making sure that your old data matches reality, and then running the model forward in time, and there's problems with that, acknowledged problems with that. The other thing you can do about error is to take the 6 models and see if they're all in agreement. They're all run by different agencies around the world using different models. So if they all agree with the direction of travel, then you can feel reasonably confident around that. So what I found was that the 6 models agreed strongly in annual changes out to 2050 and seasonal changes out to 2050, and spatial changes, they had some disagreement in extremes. And so I've only put extremes into my modelling where the models are in agreement. And there's a whole lot of detail around that, which I won't go into, but that's the basis of it. So we've got these daily river flow and wind speed records, and I've amalgamated them into the modelling regions for the energy modelling. So this is what they are. So this is quite busy. I'll talk you through this. So we've got about, I think it's about 15 hydro catchments around the country, from Purdie on the left to Waikato on the right. The black line in the middle is Cook Strait, and you can see that it's mainly getting wetter in the South Island and mainly getting drier in the North Island. This is percent changes between now and 2050. So we might expect sort of 2 to 9 or 0 to 9% increase in the South Island, and sort of 0 to 6% decrease in annual inflows between now and 2050 in the North Island. So blue is more water and red is less water. And then we've got the emissions pathways. So RCP 2.6 on the top line and RCP 8.5 on the bottom. I'm sure I don't need to explain those. I did yesterday, but I'm sure I don't need to explain RCPs here. And so I've denoted 4.5 as the most likely. Now we know a bunch of things, that the IPCC has gone to SSPs instead of RCPs. This is currently using CMIP 5 data, these projections. CMIP 6 is I'll go back a bit, coupled model into comparison project, where somebody's got all the global models and comparing them. And the last data to come out of that project was 2014, which is quite a long time ago. That's CMIP 5 data. So NIWA now has in their hands CMIP 6 data, and they are working on the regional downscaling. Sud is working on that from NIWA. So I had a chat to Abba and I said, look, I'm using old data here. How different is the new data, which she's working madly on, and it will come out in a few months. She said to me, it's not incredibly different. Just keep working on the data you've got. So that's all I've got to go on at the moment. But when CMIP 6 comes out, we'll be able to update this.
Are they using the same models?
No.
Are they going to use the same group of models? Because there's a big shift.
Yeah, I don't know
Some of
actually.
the climate sensitive
I imagine that's part of others' work, is looking at which fonts to use. Yeah, I don't know which one she's using. So current estimates are that RCP about 3.4 is about where we're headed. Of course, that could go up if we have big global unrest, and it might come down if everyone's really ambitious in their decarbonisation. But I don't have 3.4 outputs from these models, so I could use 2.6 or 4.5 as my best guess, and I've just chosen 4.5. So under that scenario, the best guess is 2 to 3% wetter in the South Island and 2 to 3% drier in the North Island. So if we look at wind, same thing. These are all wind farms, either ones that have been built. I think there's 1 or 2 that are still under construction, but White Hill and the very far south on the left, and Purdie in the far north on the right. The big picture here, so blue is more wind, red is less wind. The big picture here is windier everywhere, except the far north of the North Island, where we're going to get less wind. And that's been the same pattern in these projections for quite a long time. Looking at RCP 4.5, it's sort of, I'm looking for numbers, no, I can put it written down. So we sort of, 0 to 2% wetter generally everywhere. So that's annual projections, but we need to get more granular than that for our forecasting and our modelling. So if we look at seasonal changes, once again, a really busy picture, but sort of quite simple in a way. This is their same 10, 15 hydro catchments up the top, and every week of the year down the left-hand side, with July at the top, June at the bottom, and summer in the middle. This is percent changes between now and 2050 for each week, for each region, under a mid-range scenario. And the big things to notice are about 8% wetter in the big South Island hydro lakes in winter, drier in, what was written down, which might make it a little bit easier. Here we go. So higher river flows in winter in the South Island, drier in the summer, particularly in the east in the South Island. North Island, drier summers as well, and a little bit wetter in winter in the central and western parts of the North Island, and a little bit drier in the east of the North Island. And for wind, we can expect less windy summers and autumns and more windy winters. And this is a mid-range scenario. So if we look at a high-range scenario, it's really just the same pattern but solidified. The colours are not quite right. I should have conditionally formatted them all at the same time, and I didn't. So the colours sort of look the same, but the numbers are a little bit higher in the 8.5. So 8.5, we've got like 23% wetter in winter in the South Island hydro lakes, and about 12% drier in summer in the North Island hydro lakes. So much bigger numbers, but of course we're very unlikely to get RCP 8.5 now. And in wind speed, well, that just generally drier in the summer. Sorry, less windy in the summer and more windy in the winter. Right. So that's average changes. What about extremes? So it's really interesting, particularly in energy. Floods and droughts are really with a particular interest. Can we capture the floods, or are we going to just spill them all down the river? Are the wind speeds going to get so high that all the turbines reach cut-off speed and turn away from the wind and we end up with less wind, or can we capture that wind? So that's quite an important aspect of this. We know warmer air can carry more moisture and atmospheric circulation changes are expected, and so generally the agreement is that there's going to be larger floods in many areas and deeper and longer dry periods in others. We can expect, so this is changes over time between now and 2050 in big flood zones. So I looked at the time series heading out to 2050 and said, is the distribution staying the same, or are the floods getting bigger and the droughts getting drier, or is everything moving up, or is everything moving down? That's what I was interested in. So this is just big events, the running 95th percentile. From this, we can say that we're going to get bigger floods on the South Island. Remember that blue or green is our most likely scenario. So perhaps sort of 1 or 2% bigger floods in the North Island by 2050, in the South Island. 1 or 2% smaller floods in the North Island. Got to get my terminology right here. And then if we look at only the dry periods, so the 50th percentile of all the data going out to 2050, does it get drier dries or wetter dries? And the big pattern here is much longer, deeper droughts in the North Island, 5 to 10%, even in a low or mid-range emission scenario, and a bit of a mix of impacts in the South Island for dries. But if you can see any pattern for the dries in the South Island, it is an east-west sort of pattern where the west coast and Manapōuri are sort of might get a little bit wetter dries, but the Clutha, Pukaki and Tekapo are getting drier dries. Oh, hard to get my mouth around all that. Wind extremes. I'll put both of these up at the same time, actually. So really, wind speeds are increasing across the range. Mean wind speeds are increasing, high wind speeds are increasing, low wind speeds are increasing. The only changes to that are the far north, where high wind speeds are going to decrease. And the low wind speeds, it's a bit of a mixture, but generally the pattern is windier everywhere. And if we look at a mid-range scenario, then we're sort of looking at the blue lines, which are sort of 1% windier, so not significantly. Right, so that's all the past wind and water, the future wind and water, what happens if we bung this through the electricity system model. So I'm going to run 3 scenarios. One is using historical inflows of wind, which every energy modeler in the country is currently doing. So that's what we get, and we know what that looks like. The outputs from that model show us we need to build a couple of wind or solar farms a year. We're going to get more intermittent. We need something to firm up the intermittency. We build a bunch of batteries. We have demand response. This is what a normal energy model looks like. So that's the first scenario. The second one is those middle of the road emissions, wind and water changes. And the third scenario is the high emissions scenario, just to show what an extreme example looks like. So I'm going to talk to you about these aspects of the electricity system. So if we put these climate change impacts to wind and water in the model, what happens to hydro storage? What happens to spill? Do we just spill all that extra water down the river, or can we capture it? Price volatility, by moving water from summer to winter as we are doing, do we reduce the price volatility? System security, so system shortages, demand response and battery usage, do they go up or down? And generation capacity, how much new kit do we have to build? Does this make much difference to that? So those are the questions, and let's get on and answer them. So on the, yeah.
What do you use for your demand side of the equation scenarios?
Just a demand forecast, but it is quite detailed. So it includes increases to irrigation load, increases to air conditioning load, decreases to heating load, spatially around the country. So the model that I use is really detailed. It's got 166 grid exit points where you can model at each grid exit point. And the temporal scale is ostensibly weekly out to 2050. But within that week, I have a 15 load duration curve. So I can focus in on the peak hour and the trough hour in every week and say what's happening. And that's quite useful for particularly peak hours in the late 2040s. It's useful to look at that. I'm not talking about peak hours here. I only had 20 minutes to talk it downstream, so I didn't have time to go into that. But that's what I'll be writing up for my final report for Deep South and publishing. Yeah, but it is quite detailed. And it's got, it's based on population growth. It's based on technology changes, efficiency gains. There's quite a lot of work has been gone into it. And that's the advantage of using this model that's being used in industry, that it's really, really up to date. The thing that's changed radically in the model, which I haven't been able to keep up to date, is costs of builds. So it's an economic model. If the prices get too high in the model, I go and build a bit of kit to bring the prices down. And prices to build have changed so much through COVID that I just can't really keep up with it. So what I do now is just it's reasonably up to date, and then I just change something and look at the difference in capacity and the difference in costs, capital costs, rather than giving absolute numbers. And that's becoming a bit more normal. The price to build a wind farm went up 12% in 1 year during COVID. So it's very hard to, and supply chain issues, it's quite hard to get that right. But anyway, there's a lot of detailed information in there, background. That you know, when I write a paper on this stuff, it's quite hard because you really need like this much to talk about the detail in the model. But what I want to say is, well, I've got a black box and then I throw something into it and what comes out the side, but the detail in the model is huge. Okay, so let's look at hydro storage. So on the left, we have total New Zealand hydro storage weekly from now till 2050 under the historical inflow and wind. And you can see the seasonal cycle clearly there. The other thing that happens for both these scenarios is that it's that hydro storage gets higher. So the model holds the hydro storage higher over time in all scenarios. And so that's not to do with changing wind and water that I'm putting in. It's just the background model. And that's mainly due to increasing intermittency of supply from renewables, because the model is penalised for running out of water. So there are stronger and stronger penalties as the national storage dips really low. And the model will do anything it can to get that up again. So that's why it tends to hold the model higher as things become more intermittent. So that they look the same, these two scenarios. The only difference really is that there's a 6% less range in the 2040s in the hydro storage. And that is actually mainly just a less time at low storage. And that's decreasing range. And that's generally because we're shifting that water from summer when it used to arrive to winter when we need it more. So the lakes don't go quite so late in winter. No, because now I'm talking about the difference between these two. So the one on the left has just got historical inflows.
Oh, yeah, no.
Holding the same height. Sorry, yes. Yeah, but that's what I mean. So there's
Yeah.
increasing intermittency of renewables because we don't have the thermal backup to.
Yeah, so you take it.
Yeah. Yeah, so the wind's all going up and down like this, and matching that to demand is very, very difficult. Whereas at the moment, if the wind all dies away and the lakes are a bit low, you just flick on a coal plant and everything's sweet. So that intermittency is going to go up and down. You see that in storage and in prices, that things just become a lot more volatile. Yeah. And so any energy model has firming in it. What I've got in here is a bunch of demand response. So that's big industry and households, everyone's hot water being turned off between 6 and 8 p.m. in winter. So that, and a whole lot of stuff like that. You know, people will come home in 2050 and plug their EV in, but it won't turn on, it won't start charging till 10 p.m. because we need that power of that evening peak in winter. I also have batteries, grid scale batteries in here, which are being built. They're expensive. And I've also sneakily, well, I haven't, me and my modelling friends snuck a bit of extra storage in Hawea and Taupo, which is a bit, as soon as Onslow left, you know, it became extremely unlikely, then we need to firm up somehow. So, and you don't have many choices for firming. So grid scale batteries are huge and they're great for firming 4 hours. You can shift power from the middle of the day when the sun's shining on your solar panels to the evening peak in winter where the sun's gone down, but you need that massive load. They're great for that, but they're not good for shifting between seasons when we've got no hydro storage. So firming is a massive problem, and that was reflected at the conference yesterday. A lot to talk about. Yeah, what are we going to firm up the intermittency with? So that's really why the lakes are held higher, and whether that will actually happen, I don't know, and we need to find some firming solutions. Yeah. So let's look at spill. This is quite interesting. This is the average hydro spill. Oh, that title's wrong. Sorry, this is the 2040s for the historical run, the 4.5 run and the 8.5 run. And the 4.5 run has 2% more spill overall over the 2040s. And the 8.5 run has 5% more spill. And so this is, deleted my notes, but anyway, once again, so we're going to get bigger floods, the lakes are going to be higher, and so we're going to be less able to capture those floods and we're going to spill it down the river. Another interesting aspect about spill is this. So in 2022, we spill from November to May, but in 2050, under a mid-range scenario, we spill any time of year. And that's because we've reduced the range of our hydro lakes there. We've moved that water from summer to winter when we mainly need it, but it means the lakes are higher and there's bigger floods coming in. So we can spill at any time. Whereas at the moment, we generally just spill in summer when the late summer when the hydro lakes are really high. So it's just another.
Done by Alex.
Yeah. Yeah. So price, so the model optimizes around price. So as I said, if things get expensive, then I just build another wind farm in the model and prices drop down again. And I can only do that to a degree because I have to make all the wind farms and solar farms make money. I can't just build them all to solve my problem. I can't just build 100 wind farms and hope that something's spinning at some point. Because they have to make money in the model. So generally, I'm optimizing around price. The average price is about the same in all of these model runs. But what is different, and the reason I'm putting this up here, is to show you that increasing price volatility for a start in both model runs, but also just in the more extreme prices in the 2040s, the climate change one has more extreme prices by about 25%. 25% higher weekly maximum prices in the 2040s. So that's it's interesting. I wasn't quite sure why this came out like it did, because I'm moving water from summer to winter. At the moment we get all our water in summer, and we have to store it right through to winter. And the lakes go really low in winter and really high in summer, and that range is decreasing a little bit. So I would have thought that, obviously they're both more volatile through time as we get more wind and solar, and it's all going on and off and on and off. Prices are going up and down and up and down. That makes sense. But the fact that the climate change one is more volatile pricing, was surprising to me. And I think it's just two things: the bigger floods in the South Island and the bigger droughts in the North Island mean that those prices go up and down more in the climate change one. So this is just about the end. So this is changes to generation capacity. How much do we have to build? So we have to build effectively 2 wind or solar farms a year for the next 30 years to supply what we think is going to happen to demand through electrification. And that is, I've heard a lot of different numbers, somewhere between 40 and 50 wind farms, let's say. And under our mid-range scenario, we build 1 less wind farm, and under our 8.5 projections, about 4 less wind farms out of that 45, let's say. So it's not a radical change. It is a little bit different. And there's no surprises here, really. We're putting more water into the system. We're shifting it from summer to winter when we need it a bit more. We've got a bit more wind and a bit more water, therefore we have to build less spinny things. And that sort of makes sense. System security is decreased in the climate change scenarios. So vol is value of lost load. It's an indicative thing in the model where it's the last cab off the rank. So we have things are getting short. The government calls on everyone to have a shortage. There's a shortage campaign. They ask everyone to switch things off. We use the contingent storage at the bottom of the lakes, which we're not normally allowed to use. We go into them. And the very last thing is vol, which is value of lost load, is a thing which is big things are going to turn off. Industry's going to turn off. How much does it cost of this? So that's what vol is. And that's called on less often in these climate change scenarios. We dispatch less demand response and we use batteries less. We spill more and we generate more because we've got more hydro, we do more hydro generation. So those are all fairly logical. They are small numbers, but if you think that we're ostensibly going to spend $42 billion on capital costs building new wind and solar in the next, between now and 2030, which is a number that came out of the Boston Consulting Group report, or a number that was bandied around yesterday was 150 billion on new kit by 2050, then dropping 2% of that actually does become reasonably significant. So that's why this data sort of does need to get put into these national electricity models that are being run around the country by MB and the big gentailers. And they've all asked me for this data, so it'll all go in there. But the upshot is it's these small things, we need to know about them, but they're not going to make, it's not too scary, I guess is the way to think of it. So just in summary, climate change impacts on the fuel side of our electricity generation is a fairly good news story out to mid-century. We're going to get a bit more water in the big South Island hydro lakes, a bit more wind in the south, and it's generally going to arrive more when we want it in winter, resulting in slightly less system shortage, but there's going to be bigger droughts in the north. Unfortunately, we're going to spill a bit more renewable fuel as we hold our lakes higher due to increasing intermittency. The range of storage fluctuations will get narrower as a bit of incoming water moves from summer to winter, but the generally higher lake levels will make it hard to capture those bigger floods that we're likely to see in the South Island. We can build a bit less capacity because of the increased water and wind, but not much. It would be useful for energy planners to include these projections to some degree in their modelling. And in addition, some allowance for changes to water in particular over the last century will lead to better planning of energy on short to medium time scales. And I'm running some workshops on that for a bunch of energy people in the next couple of months. And the impact of climate cycles such as the IPO will have measurable effects on the receipt of water and wind by the electricity system, and this may have ramifications for return on investment of new builds over the next couple of decades. That's it.
Brilliant. Thank you, Jen. There's a lot in there. Some really impressive work.
Yeah, thank you.
Some quite useful insights. to
Yeah.
look at. Are there any questions from people? I've got a couple, but I just want to make sure. Any online? Put your hand up virtually if you're. No, okay, I'll kick off with one then. You talked about Onslow, and it sounds like what you've modelled here, that climate change doesn't actually have much. It's not so much a climate change question where you might build Onslow or not. It's more a generic system feature.
Yeah, I mean, it's the downstream effects. So we've got climate change. We need to decarbonise. We're going to build a whole lot of intermittent renewables and get rid of our lovely thermal.
Yeah.
When I say lovely, I mean our firmed dispatchable power. We therefore need some firm dispatchable power or some storage. We absolutely need those.
Yeah.
We can either build a whole lot more geothermal, except what do you know, we've got no more sites, or we can build some storage. Batteries are only good for short storage, so we need something. Pumped storage would solve it. The minute the price went to 15 billion, I became a lot less keen on it. But it would have been a big sledgehammer that sort of solved all our problems, if you like, a big expensive sledgehammer.
But from this, can you get an idea of whether that $15 billion price tag is actually cost effective in the long run versus what some of these other things?
No, and nobody knows that. So the New Zealand Battery Project was working on that very question: is if we build something this massive, where does it sit in the electricity market? How do you plonk something that enormous in the electricity market? And the answer was probably that the government would own it and then sell little bits of power out to gentailers. So that was one thing, but also return on investment for something like 15 billion. How do you get your money back as a government shareholder in that? And that's what they were working on. And when the new government came in and that was scrapped instantly, it was a 4-year project and they had 6 months to go before they were delivering their final report. And the minister just came in and said, stop. And so I was interviewed by RNZ at the time, and they said, Jen Purdie's really into Onslow. And I said, I'm not really into Onslow. I'm really into the New Zealand Battery Project being allowed to finish their analysis and tell us what the solution is to dry air risk, which we don't now have one for. So, and there was talk of that at the conference yesterday. So Onslow's gone, what's solving the dry air risk? And nobody knows, really. I mean, there's the choice between, there was 2 options that the battery project was investigating. One was Onslow and one was the portfolio approach. And the portfolio approach is a whole lot of little things. So it's really organised demand response. And that's starting to happen. TY now has an arrangement to turn off where there's system problems. I just did some modelling with a student, which I'm going to publish this year, which is that we said, okay, TY offers significant demand response. Southern Green Hydrogen is a 600 megawatt plant, which might be built in Southland. They are built, then they offer demand response. We have 10 data centres. They can all offer a little bit of demand response. They don't do much. And NZ Steel's now offering demand response. Does that solve our problem? Can that be used instead of Onslow? And the answer was no. You build all these really big plants, they create a problem, then they solve their own problem by providing demand response, still not providing the main firming for all this intermittency. So that question's still out there. And I have more and more over the years become a proponent of a little bit of gas being left in for at least the next 15 years until we can come up with a solution.
Just chuck another meter on hardware.
Yeah, absolutely. That's one solution. Yeah.
But it's the easiest, if
it's not
hardware's easiest because it doesn't have the low-lying organisation around it. So.
It's already got a lot of and Taupo could go up a little bit too. but that's not enough to solve it. Yeah, those are they would help, but they wouldn't offset Onslow. Onslow's massive.
But also got messier as soon as the day-night differential starts disappearing as well, right?
What's that saying?
That once you start to get less of a day-night differential in pricing,
Yeah.
the Onslow model is less appealing.
Well, we're still going to have a massive day-night differential though.
Right.
And Onslow is a seasonal solver.
Yeah.
But it also solves the short-term problem because it comes in winter and generates flat out, which means you don't have the intermittency problem so much with the wind and solar. You do still have the day-night differential. In fact, I did a study with another student where we put all the EV charging is going to be massive, and we put all that EV charging by 2050 into the nighttime. Said, well, that solved our problem. But no, of course it didn't, because all your solar became unprofitable. So then we said, okay, well, ideally, all those EVs would charge as the clouds came across, all the EV charging would stop, and then as the sun came out, all the EV charging would go up. But practically, that's really hard to make happen. So, yeah, no, Onslow would have solved everything, but $15 billion is just huge. I mean, Snowy Hydro has just been completed, Snowy 2, and it started at 1 billion and ended up at 10 billion or something. Yeah, by the time they finished it. So chances are the 15 billion might have blown out as well. Yeah, nobody has the answer, but it's an interesting problem.
That's a problem that the ministry will have to think about, regardless of whether battery electric gets out.
Yeah, but there's a big gap because so the MB is working on a New Zealand energy strategy, which we've never had, and that's coming out this year. But I've seen some previews of that, and it's not detailed at all. It's just quite general. So unless they, yeah, so at the moment, it's actually, from what I've seen, it's not going to offer any wonderful solutions. But I think the government seems to be just saying, right, we'll get rid of that and get rid of that, but we haven't seen what the alternatives are yet.
With a drier north and a wetter south, do you start to run into HVDC problems?
Yeah, I mean, Transpower's got an incredible build program out to 2050, and they're keeping ahead of all that. They've got upgrades for the DC planned, and no, we don't see constraints. I've got upgrades for the DC in the model, and we don't see many constraints, which is great. In this, I haven't seen constraints. Transpower's biggest problem is distributed energy, wind farms wanting connections, an offshore wind farm off Purdie wanting to hook into the grid. That's what their focus is on. They're carrying on upgrading the DC. But a lot of at the moment, all the power's in the south and the demand's in the north, but a lot of the new solar that's going to be built is in the North Island and wind. So that's going to become less of a problem, I think. Yeah, and we're not building any new big hydro anywhere now that Onslow's not happening. So, yeah, I think that's it. The DC doesn't seem to be a problem for now. Yeah.
We're at 1:57. Just one final quick question, unless someone else jump in, is where does distributed micro generation, rooftop solar, so on fit into this?
Yeah, I mean, it's sort of been touted as the great solution, but solar for a start is not the total solution, because we need power. Our big problem is between 6 and 8 p.m. in the middle of winter, and there's no solar there. So solar is only useful with batteries. If you've got it with batteries, it's fantastic. And it's proliferating hugely. We need mechanisms like this idea of this virtual power plant to sort of band together. And people are doing that. Like we heard from some companies at the conference who were working with Solar City. There's a company that was working with Solar City. They got 30 or 40 of their customers with solar. They put a battery in the middle of them, and they offered them in as reserve at times when it was needed in the market, and were making money, making a profit themselves, and giving money to the rooftop solar people. So that is starting to grow, and that's really exciting. That's cool. Because like I went to Downstream 3 years ago, I think, and the big question was, what the hell do we do about distributed energy? Because it's so in that 3-year period, solutions are starting to pop up. Yeah. And I put a bid in with a bunch of people for some funding. We're going to try and model amalgamate because we can't model individual rooftop solar in this model. It's not granular enough, but I do have a representation of of rooftop solar amalgamated. We're going to try and amalgamate rooftop solar and batteries into VPPs, virtual power plants, and then offer them into the model market and see if we can sort of get some feeling on how that's going to grow and what it's going to look like. Right down to the level of, you know, when one street gets solar, when one person on a street gets solar, everyone else does. So it's a funny, that's how it grows. Yeah, same with EVs. Yeah. So that sort of stuff is, yeah, we're having a look at.
Keeping up the Jones.
Yeah.
Well, hey, thank you very much. Really appreciate
No worries.
you coming in and sharing this with us, Jen.
Thank you. Yeah.
Fascinating work. Look forward to the publications coming out.
Yep.
So with that, I'll close us off with the karakia. Te mauri o te hu ka ia, te wānanga o te hu ka ia. Ko ki papa, ko ki rau. Yeah, yeah. Thank you very much, Jen.
Oh.
Cheers.